All right, last time, this is about where we left off, right? We were talking about full adders, right? Yeah? I can't remember what I did yesterday anymore. So there was the idea of the full adder, and we did take our time to talk about, like, well, when you look at these two tables, the sum bit is just an even odd count. If it's an even number of ones on the input, the sum is 0. If it's an odd number, it's 1. So all the times there's 2, you can see we have a 0 or a 0, there's a 0. And 3 or 1, we see a 1 in the sum bit. And then the spoiler, the carry out was, first of all, obviously 2. Remember the fact that we have a carry in here. And here it's if this is on and this is on, or this is on and this is on, or if this is on and this is on, or if all three, I guess, right?
That was already included in one of the things you said.
So that's what we've broken them down to. But we were able to simplify them a little bit more by saying, well, okay, if A and B are both 1, or if the sum of A and B is 1 and C is 1, which is just a handy way of kind of combining. So we simplified the circuit a little bit. We could have had it a little bit more long form by include all the ands and oring them together, but whatever. What's nice about this design, first of all, unlike the half adder, which has no carry in, what's nice about this design is it scales forever. Right? This, of course, will only add 2 one-bit numbers together, but we have the ability to have a carry in and it produces a carry out. Meaning all we have to do is chain the carry out into the carry in of any subsequent full adder. All right? So this design here, we see 0, 1, 2, 3, and a carry out. This will add 2 4-bit numbers together. But also notice that there is a carry in to this whole design. Which means, like, I mean, the whole idea of the scaling is like I can chain these whole 4-bit adders together and create like an 8-bit adder or a whatever. Like the idea is I can just chain these on forever. And we have a nice way to be like, well, was there a carry in or not into this whole sequence? That carry in will be a handy little feature that we have later. But right now you might think like, okay, whatever. I'm adding 2 4-bit numbers together and I've got this first carry in. Doesn't really serve much of a purpose, but yeah, as it stands, it doesn't really. But, you know, it exists. What I mean is, assuming I've got like integers, right? We're not talking about floating point numbers and we're only dealing with like positive integers or something. If I have like 0, nice. Let's try 0, 1, 1, 0, 0, 0, 1, 1 or something, right? Like, whenever you're adding numbers together, the least significant bit, there's no carry in to that bit. I mean, there's no decimals here to carry into, right? Meaning like, well, what's the purpose? Like, consider like all the carries are like here, right? They may or may not exist, right? So that's a 1, 0, there's a carry, 0, 1, right? But this one, it could never really exist, right? That's my point. So we've got that carry in bit to this whole design. It can never really exist, but you know, it's there. I could take a 4-bit adder and chain it to another 4-bit adder where its carry then goes into this one. So it's there for a design for, you know, for the scaling, right? It does exist even though we're not really using it here. But this is it. This is 2 4-bit numbers being added together, which is really nice. It's just 4 full adders chained together. Let's open up digital. Here I was scaling, like, doing 2, but let's, so there's the design. We zoom in. What were the 2 numbers? 0, 1, 1, 0. 0, 1, 1, 0, and 0, 0, 1, 1. We have 0, What? Oh, I've got the wrong number. What? 0, 0. Oh. 0, 0, 1, 1. I was going the wrong way. I was looking this way, not this way. So we see 1. Sheesh. 0, 0, 1. And the carry bit is off. If we want to have some fun, let's just add a 1 to here. And we can see that, in fact, the carry bit goes high, which makes good sense, right? And we never need another carry bit because the most we could add together is the two biggest 4-bit numbers we could add together are 15 and 15, which you put together is 30, which could be representable by one more bit. We would never need more than one more bit, right? We've established this last time. If you don't remember, we were talking about it somewhere around here. Yeah, in general, when adding two n-bit numbers together, n plus 1 bits is sufficient to output the correct sum. Remember, adding a bit doubles the number of representable values. Consider the following. Yeah, whatever. We don't need more details than that, right? Cool. So any questions about this full adder idea? This is how, like, okay, we could chain them together, but, that doesn't, whatever. But if we go into here and we go arithmetic, adder. Okay, let's zoom in. This is what we see. A and B are the two numbers being added together, the two integers. C is some carry in. S is their sum, and then there's a carry out bit, right? Like if I have a 4-bit bus and that carry out bit is high, it's kind of like lost. Like if I have 1, 1, 1, 1 plus 0, 0, 0, 1, what do I get? I get 1, 0, 0, 0, 0. But if I only have 4 bits, as far as like the computer's concerned, oh, the sum of these two numbers was 0. But that carry bit was high. So like, if this is a 4-bit, like imagine there's a bus and it's got 4-bit, it's 4 bits wide. I can't put 5 bits on a 4-bit signal. So this carry out needs to be like its own separate line. Okay? I could chain these together pretty easily. Right? I would just have to go like, okay, let's make it a little. Right? And then I could keep doing that. You could think of this as a 1-bit full adder. I could chain them together. But do note that we can go in here and be like, well, how many data bits are there? 4. Great. Now it's a 4-bit adder. All right? Yeah? Happy, sad? Let's see if I can get this working real quickly here. Oh, what did I do wrong? Do I really need a C in? Sometimes you get lucky where you can kind of ignore things, but I guess this one really needs, I guess that makes sense, right? What's the carry in? It's either a 0 or a 1. Wires? Constant. There. This is ugly, I know. Don't ever make your designs look like this. If you submit something like this, the marker will, I'll tell them to let loose, right? All right. Oh, now what? 4-bit, oh, these need to be 4 bits, right? 4. 4. 4, but of course the carry bit is only a 1. Let's try now. Perfect. So let's add the number F and the number 1. And apparently the F didn't go through properly. F Fine. Oh, all right. There. So what's the sum? Well, apparently it's 0, but the carry bit is high, right? If we made this, let's make it 3, well, we should see 2 because the number is, right? Is that right? Yeah. Right? So we see 2 and then that carry bit. That's what we're seeing here. Happy, sad? What do we think? Okie dokie. Any other last chance about adders? Look, like I was saying last time, we have a way to store data, we have a way to move data around the system, and we have a way to do arithmetic now. Great. Addition. If you can do addition, you can do a lot of things. However, right now we've only talked about integers. In fact, we've only talked about positive integers. Okay? And you might not realize this, but yeah, we kind of need negative numbers here. But how do we represent negative numbers? Well, at the end of the day, this is a bit of a design decision. Now, there is a really good design that we're going to work towards. But at the end of the day, this is a bit of a design decision. How are we going to represent negative numbers? I mean, I know what binary is. Could I just do like, okay, if I have the number like 10, right, and I want negative 10, well, just, negative 10, right? Yeah. But I mean, like, what is this? I guess, maybe we could have like a sign bit. Yeah. We have like another bit. Maybe that can mean 1 or 0. I don't know. Will that work? Will it not? I don't know. We'll have to figure something out here. So as long as enough bits are available, any possible integer, and 0 can be represented with n bits, the total number, the number 0 through 2 to the n minus 1, the reason we have the minus 1 is because we include 0. There will be a total of 2 to the n unique numbers, right? Can be represented. This would be what we call an unsigned integer if we were representing the numbers 0 through 2 to the n minus 1. Okay? However, can negative numbers, what are we going to do? Well, a sign bit, like we just kind of talked about, a sign bit. So all binary numbers so far have been unsigned. They can only represent positive integers and 0. So consider the following table with the number 5 represented as an 8-bit binary number. Okay, here we go. So here's an 8-bit binary number. Each bit's place is like value is represented here, right? If this was decimal, we'd have 1, 10, 100, 1,000, 10,000, 100,000, a million, 10 million, right? But here we have just binary, so it just doubles up as we go down. And we have a 1 and a 1, and a 1 and a 4, so we have a total of 5. This means 5. The zeros are included all the way up to 128. So to determine, what the number represents, you add the place value of each bit, that is 1. Technically, you would take the value of each digit and multiply it by like 2 to the power of whatever its position, like 4. But I mean, 1 times whatever is always whatever, right? So we kind of forget that part. But if you were doing base conversions, don't forget that point, right? You would do, it's like, well, if I have 2 10s, that's 20, right? 2 times 10, right? So to determine it, you just, add the columns that are 1s. 4 and a 1 is a 5. So as discussed in an early topic, this works the same with base 10 numbers. All of these rules are the same, it's just what base are we working in. Addition in binary also works the same way as in base 10, but with only 2 symbols. Add up the values. So here's I'm adding the numbers 92 and 154, right? That's what I want to do. If I'm doing it in decimal, well, how do I do it? Well, I take 4 and 2, well, that's a 6. 9 and 5, that's 14, but I can only put the tens value, the 4 there, and I carry that 1, and I get 1 plus 1, and I get a 2. Right? Right. It works the same way in binary. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0, but we carry the 1. 1 plus 1 is 3. 1, carry the 1. 1 plus 0 is 1. 1. Uh-oh. Now, we can't have that. We lose that last bit, right? 1, 2, 3, 4, 5, 6, 7, 8. We would need that 9th bit to represent 200 and... does that make sense? 1, 2, 3, 4, 5, 6, 7. 1, what is 1, 1, 1, 1, 0, 1, 1, 0? Something feels wrong. Am I crazy? Oh, what was it? 1, 1, 1, shoot. 1, 1, 1, 1, 1, 1, 1, 1, 0, 1, 1, 0. Two 46, 246. Oh, am I just, okay, hold on. Carry the 1. No, there's no carry. And then it's a 1, and then it's a 1. Yeah, okay, I don't know what I'm doing wrong here. I don't know why I thought there was a carry on the last one. My eyes, oh. Everything's fine, don't worry. All right, the above table shows addition of two numbers in binary and decimal. The left side is binary and the right is decimal. Cool? Happy? Yeah? There we go. As a way to show, I've added another row called carry, right, where the carry was coming over. A simple way to represent negative numbers is to use the most significant bit as a sign bit. So consider the number 5. 0, 0, 0, 0, 0, 1, 0, 1. All right? We could use a sign bit. Well, so to represent negative 5, we could use a 1 in the most significant bit's position. So negative 5 could be 1, 0, 0, 0, 0, 1, 0, 1. Okay? Now, you might say, yeah, but that's also the value of 128 plus 5, so 133, right? But yeah, but we'd have to know what we're dealing with. Is it an unsigned integer or is it a signed integer? Not a big deal. We just have to pay attention to what our data is. And if you think like, well, that's kind of a pain. Well, yeah, you're right, but I mean, that's what our computers have to do all the time when it comes to types, right? Is it a character? What does it mean? What do I decode this value to? Is it an integer? Well, if it's an integer, this is what it is. Is it a signed integer? Ah, well, that's what this is. It all depends on what the data is. Remember the difference between the encoding and the decoding, what the data is and what it means. That was that whole information versus data, right? Since the most significant bit is used as a sign, fewer positions are available, though. If the 128-bit represents a negative number, that means I suddenly can't represent the numbers 128 through 255, right? Because, well, that means negative, right? So now, though, let's go back to a 4-bit example where I can show all combinations. There's 16 unique values, right? I want to make my point clear. If I have like 1111 did mean 15. But if we are saying the most significant bit means sign, suddenly it's, well, whatever this is, oh, and it's negative. Okay? So it might feel like, okay, well, we lost all those numbers. Yes, but we gained negative numbers. Before I had 0 through 15. Now I have negative 7 to 7. Right? Yeah? Because 1, 1, 1, 1 is negative 7. 1, 1, 1, 0 is negative 6. You just basically look at what is the number. 4 plus 2 is 6. Add a 1, so it's negative. 1, 0, 1, 4 and 1, well, that's 5. Add the 1, it's negative. And so on and so on and so on. So now we have a solution. But what do you notice in this table? It's not a big deal, but you might notice it. What do you notice? Yeah, we've got 2 zeros. 0, 0, 0, 0, and 1, 0, 0, 0. Now, you might say, okay, is that really a big deal? I can write 0, I can write negative 0, it doesn't really matter. Yeah, but first of all, there's no real meaning to negative 0. 0 is just 0. It doesn't really have a sign, it's just there. So, okay. And there's also like a problem of like having, okay, we can kind of dismiss the whole like negative 0, okay, who cares, whatever. But remember, we are dealing with a very limited system, right? I have 4 bits, I can represent 16 unique values, but I've lost one. Because I have 16 unique bit patterns, right? And I have 2 bit patterns meaning the same thing. So that's kind of annoying, right? Right? And yeah, what else? There are some other issues. Okay, so first, one may have started to notice some issues with the strategy. There are 2 patterns that represent 0. One is negative. This does not really have any meaning for integers. Another issue is the pattern from is that the pattern for the numbers changes depending on the number of bits. Yes, so this one's kind of an annoyance too. If I ask you, based on everything I've said so far, what is negative 5? Somebody tell me, what do I write down to say negative 5? 1, 1, 0, 1. Why wasn't it 1, 0, 0, 0, 0, 1, 0, 1? Yeah. Like the bit position depends on, well, how many bits are we dealing with? That's not that big of a deal, but there's a bit of a, we can kind of get an appreciation for, okay, that's kind of funny. But consider the 4-bit binary number and the 8-bit number. Yeah, okay, both represent negative 5, yet they have different bit patterns, right? And finally, and perhaps the big one is, well, when we add negative numbers with decimal, 5 plus negative 5 is 0, right? Right? Like, you do addition on the negative numbers and you just effectively do subtraction, right? So if you were to try to add negative numbers with a sign bit, something weird happens, right? So let's just do addition, right? Okay, 1 and 1, well, it's 0, 1. Okay, that's a 1. 0, carry the 1. 1, 0, 1. 0, carry the 1. 1. So apparently, 5 plus negative 5 is 2. That makes sense, right? Of course not. That's ridiculous. It doesn't make any sense. Well, really, actually, I guess it's like negative 2 because the most significant bit is a 1. But then again, that was a carry bit. So is it negative 2 or is it 8? Is it 10? I don't know what's going on, right? Something funny here. Even if one ignores the fact that the sign bit got carried to a 5th bit, because that's what happened here, right? Is this was like a sign bit. It didn't really have a value. And yet we added it like it did. Something funny happened, right? So we just did addition with with like a negative number, how we encoded a negative number, and it just doesn't work. Okay? A potential alternative. Okay, before I carry on, any questions about this idea of a sign bit? I want to be clear that if you really wanted to make a sign bit work for your computer, you could. You could hack this hardware away to make it do its thing. But there might be better alternatives that we're going to come to. And if we really spent the time, like if I constructed a lab or I gave you an assignment where I kind of like posed a series of questions to you, I'm willing to bet you could kind of like get to 2's complement on your own. You can kind of figure it out. Maybe not, maybe, I don't know, but we could start to discover the problems and maybe some solutions. So what we can do as a step in the direction into addressing these issues is we can do 1's complement. All right, the strategy is similar to a sign bit, but with 1's complement, all bits are flipped for the negative numbers. Take the complement of each bit. Okay? So, if I had the number 7, and I want to represent it as a negative number, you just not. You do like bitwise not. Okay? Negative 7 would be 1, 0, 0, 0. Okay? 6 wouldn't be 0, 1, 1, 0. It would be 1, 0, 0, 1. You just invert everything. Okay? We're literally just doing binary, like bitwise not. Okay? Any questions about what this table is showing? Okay, It's simple to identify negative numbers. We still have that 1 in the most significant bit location. So you can look at a bit pattern. If you know it's a signed integer, right? If I know that I've got a bit pattern that is a signed integer, I don't know, is it actually a negative number or a positive number? I don't know. But by looking at it, I can quickly tell if it is, because the most significant bit is a 1, and that tells me something. It's not a sign bit, but by virtue of like 1's complement, it effectively is a sign bit. Okay? But the issue of the pattern for negative numbers changing dependent on the number of bits, like it's somewhat resolved. With 3 bits, negative 3 is represented by 1, 0, 0. With 4 bits, negative 3 is 1, 1, 0, 0. Do you see what I mean? How like, well, the pattern changes. Remember with the sign bit, how this was 5, this was negative 5, this was negative 5? The difference here would be, I didn't leave enough space, but so like there still is, but like instead of an infinite number of zeros out front, when it's a negative, we think of it as an infinite number of 1s out front. So, you know, it's the patterns are different, but they're actually kind of like less different in a weird way. You see what I mean? Yeah, as opposed to an infinite number of zeros. Cool. But what are the problems or limitations? Well, we still have that funny oddity of having 2 patterns for 0. Okay? And again, you might say, okay, how big of a deal is this? And in the grand scheme of things, in an abstract mathematical way, does it really matter? I guess not. But when it comes to like the engineering hardware limitations we have on our systems, does it matter? Kinda, yeah, we're wasting space. Further, addition with negative numbers is still not quite right. So, okay, if I do 5 plus negative 5, right? What do we get? Well, we get 1, 1, 1, 1. Well, that was negative 0. It's still 0. Great. But it worked. Look at that. So addition of a negative number, as it's encoded, does subtraction. 5 plus minus 5 better give us 0. It gave us negative 0, whatever, but you know, it's still a 0. In fact, maybe that's valuable. Knowing it's negative 0, we'd be like, well, we got this by doing like subtraction. I don't know, right? But Right? Right? With binary, what do I have here? With binary addition in a fixed number of bits, any carry that results in an overflow will ultimately be ignored. Like I was saying, we talked about this before, right? For example, consider the 4-bit number 7 plus 1. The result is clearly 8, but since there are only 4 bits available, the overflow value is lost and the result would actually be 0. This was that whole carry bit thing, right? Now, if we carry on, though, with doing addition with negative numbers, okay, 5 plus minus 3 should give me 2, right? Well, what do we get? 1, 0, carry the 1, carry the 1. Oh, we ignore this, but we get back 1. 5 plus negative 3 is 1. So close, right? Ugh. Shoot. Well, maybe we got unlucky. Let's try another number, right? Negative 2 plus 6. All right, so just add them together. So this is the negative 2. 1, 0, 1, 1, 1, 1, 0, carry the 1. 1, 1, 0, carry the 1, ignore it. And what do we get here? 3. Negative 2 plus 6 is 3. No, that's not quite right. It should be 4, right? Adding negative binary numbers, and what do we got down here? So this was a positive plus a negative. This is a negative plus a positive, and let's, two negatives, right? Negative 4 plus negative 2, well, if we do that out, 1 plus 1, 0, carry the 1. 1, 1, 0, carry the 1, 0, carry the 1, 1, carry the 1, we'll ignore it. 1, 0, 0, that's negative 7. Negative 4 plus negative 2 is negative 7. But it's so close, right? How much are we off by here? 1. In fact, we are like 1 less than what we need it to be, right? We needed to be 4, but we got 3. We needed to be negative 6, but we got negative 7. We're always 1 lower than we need it to be. And like, you know, when you look at that table, it's kind of it's interesting that like, sure, 0 is correct, okay? 0 is fine. But like we needed 4, but we got 3. We needed 2, but we got 1. We needed negative 7, or negative 6, but we got negative 7. We needed 0 and got negative 0, which was fine. But you'll notice we are off by like 1 every time. Even though the 0 was right, it was right in a weird way though, right? You agree? It was right in that, like, well, we got this one, but there really is no such thing as negative 0. So, you know, right? So how could we fix this? Well, could we just, like, add 1? Would that work? Could we just, like, okay, look, if after doing every subtraction, we just remember to add 1, to the result, would that work?
Well, you have to figure out if the negative number you were adding was bigger than the positive.
But then again, like, I don't know. Like, let me. Let's take a moment. It's like I'm saying, do like negative 3 plus negative 1 equals, so this would give us, so I mean, really we should get negative 4, right? But I'm guessing if we did the addition with 1's complement, we'd get negative 5. So we just magically go, well, and then like, just plus 1, just add 1, just add 1, right? Now, you might also remember, though, when you're doing arithmetic, you know, like, does it matter, like, does the order, do I need to do this plus this, then plus 1? Does the order that I do in like, is negative 3 plus negative 1 plus 1, does the order in which I apply these things matter? No, I don't need to do this plus this, then this. I could do this plus this, then this. I could do this and then this. It doesn't really matter, right? Remember that. When I add the 1 doesn't actually matter. But anyways. So, okay, the fact that the overflow value is lost is important for addition of negative numbers to work. However, when looking at these results, it's clear that the addition with negative numbers just doesn't quite work. We're off by 1. Except for when the sum is 0. All results are less than 1 than they should be. In fact, that whole negative 0 thing was kind of weird, right? We were like down by 1. So instead what we do, if you want to represent a negative number, here's what we do. And yes, it is as cheesy as it sounds, but it works. You do 2's complement, which just means flip all the bits and add 1. That's it. Flip all of the bits, do the complement, and then add 1. Make it 1 bigger. However, due to the associativity property, 1 could add before any arithmetic. So what I'm saying is, like, if I was doing like 5 plus negative 3, right? I'm saying don't do this and then magically add 1 at the end. I'm saying bake in that add 1 to the negative number in and of itself. So we don't have to like remember to add 1 after doing this plus this. I'm not saying do this plus this, oh, and then add 1. I'm saying just to represent negative 3, do that whole bit flip thing and just add 1 to it before you do any arithmetic. So give me let's say the number 5, 0, 1, 0, 1, right? That's 5. I say, okay, flip every bit, 1, 0, 1, 0, and then add 1. 1, 0, 1, 1. There. That's negative 5. Am I right? 1, 0, 1, 1. I am right. Look at that. Huzzah. The number 0, okay, would be 1, 1, 1, 1. But if you add 1 to 0, well, that's 0, 1, 0, 1, 0, 1, 0, 1. Oh, 1. Who cares? It's 0, right? Like it's still, there is no. But what's cool about this is there's no negative 0. We regain that double duty pattern, or that number that had 2 things on it, and we actually just tack it on that negative 8. 1, 0, 0, 0 is negative 8. So instead of negative 7 to positive 7, we actually get one more negative number with 2's complement. When we're dealing with 2's complement, we get just one more negative number. I really want to stress again, if I'm saying, imagine we have 1's complement, and we have the number 5, 0, 1, 0, 1, and the number negative 3. And negative 3 would have been, okay, 1, 1, 0, 0, right? That's negative 3 with 1's complement, right? If we do the addition, 1, 0, 0, 1, 0, 1, right? And we get 1. But we needed 2, right? So then I'm saying just add 1 to this, right? So we would get 0, 0, 1, 0. Adding a 1 to 0, 0, 0, 1 gives me 0, 0, 1, 0. Do we agree? All I'm saying is, no, don't add the 1 post hoc. Add the 1 to the negative number pre-hoc, like before you do anything. So if we go here and be like, okay, 3 would have been flip everything, add 1, suddenly the addition magically works. Because again, it doesn't matter if we add the number before doing the addition of negative numbers or after. It doesn't matter. Addition, the order doesn't matter if it's all addition. So that turns into 0, 1, and then of course we ignore that one. And we get 2. Right? So we don't add a 1 after, we add it to, we bake it into the negative numbers. Flip all the bits, add 1. That's 2's complement. Did someone have a question on that? Notice with the encoding of negative numbers, the peculiarity of having 2 zeros is eliminated. Further, like with 1's complement, different bit length numbers don't have different bit patterns for negative numbers. Yeah, which is pretty cool, right? So remember, imagine the negative numbers have an infinite number of leading ones, and finally arithmetic with negative numbers works perfectly. Anyways, cool. I mean, this is kind of a lie. We still have the weirdness of it, but it's better than the fact that like that -5 and 5 when we just had that sign bit. It's slightly better. But we just have an infinite number of leading ones. Okay, fine. Happy, sad? It's pretty cool. So now, with 2's complement, notice how the, okay, I'm just showing a bunch of examples. We get 0. 5 plus -3, we get 2. Again, this is the 2's complement negative number. -2 and 6, -4, -6. All right, with 2's complement, notice how there's an uneven number of positive and negative numbers. It is what it is. With 4 bits, there are 7 positive numbers and 8 negative numbers. It's because of that 0, right? However, with 4 bits, there's still a total of 16 unique values. So the number of unique values stays the same with 2's complement. With 1's complement, we had 16 unique values, but we only represented 15 unique values. Similarly with the sign bit, because that whole 0 thing. All right, activity time. Show me the 2's complement table for another thing that's kind of neat to look at is if you were counting in binary. Everyone, I know you're Russian, but give me a moment here. If you were to count in binary from 0, okay, 0, 1, 2, 3, 4, 5, 6, 7, what comes after 7? 8, which is 1, 0, 0, 0. And then 1, 0, 0, 1 would be 9, and so on. But you notice that the pattern continues perfectly up here. 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, and so on. So it's kind of like you just kind of take that continued part and just dunk, put it up top, but you started at the negative whatever, which is kind of neat. Anyways, draw me a table of 2's complement numbers in an order similar to what you may or may not see on the screen. I'm going to stop recording now.